In this tutorial, we're going to just go over solubility equilibrium. So we're going to first of all understand what it is. We'll look at what we'd expect, and then we'll look at some of the practice questions. Where the first one is helping us to write the KSP expressions. The second one is going to help us determine the KSP value where we've given us the solubility. The third one is trying to talk about the cases where we've been given some initial concentrations of some ions. So we're going to understand the effect that they have on the solubility. Question 4 is now focusing on precipitation. So when do we decide, or how do we know there's going to be precipitation? So we have to use what we call the Q against what we are talking about, the KSP in this very case. Okay, so from there, again, this is another question on precipitation. Question 6 is almost dealing with precipitation, except we are trying to determine the concentrations at the equilibrium. Question 7 is focusing on determining the pH. So these are some of the things that we're going to cover in this tutorial. Okay, so basically, what is solubility equilibrium? What do we deal with under the solubility equilibrium? So solubility equilibrium is basically a type of dynamic equilibrium that exists when we have a chemical compound that is in solid state and then it gets to dissolve. So the basic idea is you have a solid, calcium carbonate, which is in solid state. So when you get to dissolve this, let's say in water, you expect that you're going to have production of what? The ions. So I have calcium. So we have calcium 2 plus, which is going to be in aqueous state, and then we have carbonate as well, which is also going to be in aqueous state. Of course, that is 2 minus. So solubility equilibrium basically is giving us, it's a chemical equilibrium where we have a solid, and the solid is partially soluble, and then so this is partially soluble. So we're going to see that in our solution there will still be a solid that is going to be present, as well as the solids are also going to be present. So now that would mean that the rate at which the backward reaction is occurring is equivalent to the forward reaction. So that is solubility equilibrium. We have a partially soluble solid being dissolved, and then when it reaches dynamic equilibrium, we refer to that as solubility equilibrium. Okay, so now that we know what solubility equilibrium is, let us try to understand what solubility is. What is solubility? So when you talk about solubility, you're just trying to estimate, or we can call solubility to be the maximum amount of solute that can do what? That is going to dissolve. So solubility is the maximum concentration of solute that can be dissolved in the solvent that we have. Okay, so this is the basic idea about solubility equilibrium. And what we can talk about is, we can even try to look at the same equation that I've given as an example and understand the way the KSP depends on what we have. So if we've done chemical equilibrium, we do understand that solids do not appear in the K expressions. So in this case, our K is referred to as the KSP, which stands for solubility product. Okay, so basically, if you look at what we have, our reactant is a solid, so we only expect our ions on the right hand side to appear in the KSP expression, just like we did under chemical equilibrium. So therefore, we're going to have calcium 2 plus, and then carbonate 2 minus. So these are the ones that are now representing the KSP expression. Okay, so we'll understand later as we look at some more complex questions on how we get to simplify this. Okay, so we'll start with the first question. The first question says, write a balanced equation for dissolution reactions and the corresponding solubility products expressions for each of the solids. So just like we know, when we're talking about solubility equilibrium, what we are talking about are solids. So all these are in solid states, as the question tells us. So I'll start with the first one. So if I got the first one, what we have is silver, and then we have C2H3O2. So that is solid. So to show that this is at one point going to reach equilibrium, we'll use those two arrows, and then we'll split this into the ions. So the only ion that we can clearly see is silver. Okay, so I have silver, which is Ag plus, and then the other substance as well. I'll write it as it is. Okay, so this is what we have in our equation. So this is a balance. Is it balanced? So it is. So we've answered the first part of the question. It says write a balanced equation for dissolution reaction, and then we need to write the KSP expression. So the KSP expression, for the sake of our understanding, in this case I'm going to use the ice table, and then on the other examples I'll not use the ice table because you're going to get the concept. So solids do not appear in the K expressions, and then for our silver, we didn't have any initial concentration, knowing that we started with a solid. So I'll put 0 there, and then just like we did under chemical equilibrium, we're going to use a variable. In this case we'll go for x. So positive x and positive x. Of course this is affected by the coefficients. So if we had the 2 there, it was going to be 2x, but in this case we just have 1s as a coefficient, so it will just be plus x, which tells us to say that as the reaction progresses, we expect that there should be an increase in the concentration of our products, meaning that part of the solid is going to be dissolving. Okay, so therefore in this case our equilibrium concentrations will just be the changes, because 0 plus x will remain the same. So therefore our KSP expression, knowing that it is dependent on the equilibrium concentrations, is just going to be x times x, which is going to give us x squared. Okay, so if you want to present your answer in a more organized manner, what can you do? You can decide to show the same ions that we are breaking down. Let me just bring that back. So you can just put it as KSP is equal to, so you know that the first x is denoting the silver, so I can just put the silver there, ion, and then multiply against the other one there. So that is also one and the same. That's what we have. Okay, so therefore as we get to look at the other solids that we're given, they're going to be very easy. So if you have aluminium hydroxide, so how do you know how to balance this? So if you have aluminium and then you have hydroxide, so what the basic idea is, this 3 is going to go there, and then what is there is going to go there. So you know that metals are going to be positives, positive ions, and then these others are going to be negatives. So therefore in this case aluminium is going to be aluminium 3 plus, and then we have hydroxide. Of course hydroxide is a common one, so it's going to have a negative there. Now is it balanced? No, we had 3 hydroxide there, so we'll put 3 there, and then aluminum will just remain the same. So of course that is in solid state, these are in aqueous states. So therefore in our KSP expression we don't expect to show the aluminum hydroxide, we'll just go for the ions on our right hand side. So now in this case you're going to pay more attention to what I'm going to show. So if we are going to write our ice table in this example, for our change, for the hydroxide it's going to be plus 3x, this one is just going to be plus x. So therefore that's why I'm putting 3 hydroxide. And of course what we know from our chemical equilibrium is every time we are doing that, we get to raise everything to their stoichiometric coefficient. So therefore this is going to be to the 3rd power. So therefore that is our KSP expression, of course in respect to the solids that we have being produced for the second one. So feel free to try out the next 2. Okay, so of course if we go to the next one, we have calcium 3, and then we have PO4 2. So this is going to be the last one I'm going to do. Of course, this is in solid state. So now, just like we said, this is supposed to exchange. So therefore, the 3 will go there, it will be 3 minus. The 2 will go there, it will be 2 plus, because metals, they carry positive charge, positive ions. Okay, so 3 minus 2 plus. So we have calcium 2 plus plus PO4, which is now 3 minus. Now, for us to balance, we need to look at the sub coefficient that we have there, the subscripts, sorry. So we have, for calcium we have a 3, and then for PO4 we have 2. So in this case we've balanced our ions in our equation. So all these are in aqueous states, very important, and therefore our KSP expression is therefore going to be equivalent to our calcium. Of course, I'll put a 3. So 3 calcium 2 plus ions, raised to the power 3, again 2 PO4 should also be raised to the power 2 from our rules under chemical equilibrium. So this is the KSP expression for the third one, and that is how you get to give a KSP expression in respect to the solids that are being produced. Okay. Question 2. Question 2, we are asked to use the data to calculate the KSP value for each solid. So the first thing that we would want to do first of all is get to write the dissolution reaction, which is very, very important. So if I look at the first one, it says calcium, and then we have C2O4 as our solid. Okay. So what do you get to do there? So if you get to write your equation there, you expect to have. Now, the funny part is you do know that calcium, of course, comes with a charge of what? 2 plus, right? And then the fact that this is separate from calcium, we expect to have a 2 outside, right? So let's try to do that. So we can have calcium, and then we can factorize the 2 there so that you have carbon dioxide in the brackets, and then you remain with a 2. It makes more sense in that case, and that's what we're going to do. Which proves to say we're going to have calcium ion reacting with carbon dioxide, right? Yeah. So therefore, we have calcium 2 plus in aqueous state with carbon dioxide in aqueous state. Okay. And then what we have, we can have these 2 on the carbon dioxide part. So this is basically very, very important for us to show. Okay, what can we say now? What can we say? So we've balanced our equation. Now, the KSP expression is going to be what? So the KSP expression is going to be dependent on this. So we have calcium 2 plus the power 1, and then we have carbon dioxide the power 2. Now, one point that I didn't make is solubility basically is going to be the same for our solids that we have. So on the part of our change, this is plus x, that is plus 2x if we are going to write our ice table. So you can clearly see that the value of x is what? Is 1 and the same. So in fact, in our KSP expression, I'm supposed to put a 2 on the carbon dioxide part because of our equation. And then what I'm going to do is I'm just going to put the values of x directly. So for calcium, we just have x. And then for 2 carbon dioxide, I'm going to put 2x. That's our change. And then it's supposed to be raised to the power 2 again. So as we get to simplify that, what we have, so our KSP expression therefore is going to be equal to x. 2x squared is the same as 4x squared, and then you have 4x to the power 3. So now the value of x is what we call the solubility. So in the question, they've given us what? They've given us the solubility, which is concentration, of course. So all you'd want to do is just substitute the given value, 4.8 by 10 to the power negative 5, and then we can now find the KSP. So grab your calculator there. 4.8 by 10 to the power negative 5 multiply by 4. So I'll repeat that again. 4.8 by 10 to the power negative 5 should be first of all raised to the third power. So the third power. And then from there, we need to multiply it by 4. So what I'm getting is a 4.42 times 10 to the power negative 13. So this is our KSP expression or value for the first part of the question. And then of course, feel free to try out the second one, which is also almost one and the same. So PB3, and then we have PO4, 2. Solid state. So what we expect to be our expression? So we have a 2 there. So the 2 is going to go on the PB there, which is yeah, and then the 3 is going to go this other side. Okay, so PB is the red, yeah, red metal. So and then we have that it's going to have a 2 plus, and then we have phosphate, which is going to have a 3 minus, and then of course the coefficients are going to depend on the subscripts. So what is a 3, and then that is a 2 for a phosphate. So therefore I'm going to use the ice table in this case so that you can now maybe get it in case you didn't get it from the first part. So solids do not appear in the KSP expression. We didn't have any initial concentrations according to the questions. The changes were 3x, 2x. This is dependent on the coefficients that we have. Equilibrium concentration is going to be given as the addition of the initial and the change, 3x and 2x respectively. And of course the KSP expression is therefore going to be 3x should be raised to a stoichiometric coefficient, which is a 3, and then 2x, which should also be raised to a stoichiometric coefficient, which is also a 2. So you have your KSP expression in terms of x, and then you can now simplify. So my advice to you is, first of all, try to simplify everything in terms of x. So 3 to the power 3 is of course going to be 27. And then of course 2x squared is going to be like 4, if I'm not mistaken. 4x squared. And then if you try to, so 3 to the power 3 again is 27. Now 27 multiplied by 4 of 108. Yeah, it's 108. So 108 x to the power 5. That's a KSP expression. You can now substitute in the equation that we have. X is denoting the solubility, so just plug in 108 multiplied by 6.2 by 10 to the power negative 12. Right? So of course to the power 5. So 6.2 by 10 to the power negative 12 raised to the power 5 multiplied by 108. So approximately our value is 9.9 by 10 to the power negative 55. That's our KSP expression, or our KSP value, that is. Moving on to the third question, it is basically the same from the second question. The only difference is we now have an initial, we've been given first of all the initial concentration of our solids in the two last in the two last questions. In the first one, it is just purely water, so which is basically going to be under the same way we are from undering what? The question 2, part 1 and 2. So Ag, silver sulfate, is a solid. So we've given us a KSP for the silver sulfate. So if we write our equation there, this is going to be silver and then sulfate. So what have I told you about the balancing part? So sulfate moves as it is. So it seems there's just a 1 there as a coefficient, right? It's as a subscript, sorry. So therefore, tells us silver is a plus, and then these two go there as a minus for the sulfate, 2 minus. So therefore we have Ag plus sulfur 2 minus. And then silver we have 2 because the subscript, so I'll put a 2 there. So we've balanced our equation there. Of course, on the right hand side what we have is in aqueous states. So they didn't even ask for us to write the dissolution reaction, so even if you don't show, there's no problem there. Now we need to calculate the solubility. What have they given us? They've given us the KSP. The KSP value has been given. And of course, if you try to draw up your ice table, so grab a pen, copy this ice table and copy for the other two so that you'll be able to see the difference that is there in terms of the presence of the ions. So where we have water, of course in every case we don't consider the solids to be part of our K expressions. So we didn't have any initial concentration of any ion in water. So we just put zeros for the initial, and then our change is going to be dependent on the coefficients. So plus 2x because of a 2, and then plus a 1 because it's just a 1 for the sulfate there. So therefore our equilibrium will remain 2x and x respectively. Writing our KSP expression, it's going to be 2x to the power 2 and then x to the power 1. So raise the equilibrium concentrations to the coefficients in the equation, and that's what we've basically done. So that is our KSP expression. So our KSP is going to be 2x squared is the same as 4x squared times x, which is going to be 4x to the power 3. Okay, so allow me to now clear this part to just help me simplify everything. So our KSP is equal to 4x to the power 3. Now we do know that x denotes what? The solubility that they want us to find. So all you'd have to do is just substitute for the KSP because the value has been given, and then we are trying to find the value of what? The value of x. So divide by 4 on both sides. After that, you can agree with me that on the right hand side you're just going to remain with x cubed. So you'd want to find the thirds, or the cube root, sorry, the cube root of both sides, so that your value of x is going to be determined. So let me just punch that. 1.2 by 10 to the power negative 5 divided by 4, and then we're trying to find the cube root there. So our value of x is going to be 1.44 times 10 to the power negative 2. So for our solubility we use molar concentration, so I'll put molar concentration. So that is our solubility for that case. So calculate the solubility of silver sulfate in each of the following. So we found the solubility of our silver sulfate. Okay, now let's try to apply the same concept on the next question. So I hope you've taken note of what we are from solving there, so that you are going to compare it with the next two. Now, the second one says calculate the solubility of silver sulfate in each of the following. So we've talked about water. We've said in water there was no presence of any ions. Now, in the next one we've been told silver nitrate. Now, silver nitrate, does it have an effect on the silver concentration, initial concentration of silver? It does. How about sulfate? Not at all. So therefore, we do know that in this case, even if we are going to write our dissolution reaction for silver nitrate, we are only going to have Ag plus and then the nitrate. So therefore, in our solution,